This is the picture of an oil pipeline 80 meters underwater and 2 meters buried under the mud. How on earth did we get this picture? Let me tell you about sub-bottom profiling. 15 major earthquakes of magnitude 7 or more happens every year on Earth. Although they are destructive and devastating for human life and properties, they give us a unique opportunity to learn about the interior of our planet. These earthquakes produce a seismic wave. A seismic wave is a low-frequency acoustic energy that travels through the Earth. Earthquakes, landslides, volcanic eruption, and nuclear explosion can cause a seismic wave. In offshore industry, we also produce similar kind of a seismic wave, albeit with a fraction of that energy produced by the earthquake. This seismic energy helps us map the seabed layers, find oil and gas, build structures, and protect our underwater lifelines. These lifelines are oil and gas pipelines and undersea communication cable that spans the entire globe. But to protect these pipelines and cables, we need to know precisely where they are, as they often get buried in the shifting sand and mud. And for that purpose, we need to use a specialized equipment that can mimic those seismic energy in a small scale. So today we are going to discuss about how our equipment can detect a pipeline or cable on the seabed or under the seabed, and it is called sub-bottom profiler. So grab a coffee and let's learn. Have you seen these pictures before? They are a graphical representation of a pipeline underwater. We use a system called sub-bottom profiler that sends acoustic pulses to the seabed. Some of the energy will bounce off and most of the energy will penetrate and continue to propagate. When the acoustic impedance of the adjacent strata changes greatly, the acoustic pulse will be reflected strongly. The pulse reflection and refraction will happen at the interface of the different contrasting medium. What it means that we have different layers, that is different composition and density of sediments on the seabed. So some of the energy pulse will reflect from the boundary between two different layers, and some energy pulse will refract and continue its downward journey, and there will always be some pulse that is reflecting back as and when the density and composition of the sediment changes. And that's what we see in our graphical representation of the refracted and reflected pulse. Now the composition of a cable or pipeline is greatly different than the surrounding seabed sediments, and we get a strong echo reflected back. So a darker line indicates a stronger reflection. A stronger reflection does not always mean that it's a rock or something solid. It simply means that its composition is denser than the surrounding general seabed. This looks and sounds very simple, right? Well, there are actually a lot goes on when we are doing sub-bottom profile survey. See, in the case of earthquake, the dominant frequencies are from 1 Hz to 0.1 Hz. But it can go as high as the audible range, that is about 20 Hz, to as low as the frequency of the free oscillation of the whole Earth with a 54-minute period. These seismic waves can go through and around the Earth multiple times, revealing what lies beneath our feet. In sub-bottom profiling, things are a little bit different. We have different frequency bands for different equipment. Some have single frequency which you can select, and some operates on multiple frequency band all at the same time. They all have different purposes and usage. These seismic waves propagate their energy in beams. Narrower the beam, the better the resolution, while a wider beam covers a larger area but with a little less resolution. A narrow beam is best when a finer details are required, like locating a cable or a pipeline. Now beam width depends on the diameter of the transducer. The smaller the diameter, the wider is the beam. Most of the survey team utilizes multiple smaller transducers in an array together. This helps narrow down the beam and concentrate the power or energy. Then again, lower frequency will have a wider beam, and higher the frequency, narrower is the beam. On the other hand, lower frequency will penetrate more into the seabed than the higher frequency. And now you are confused. What shall I choose? Well, first determine the purpose of the survey. If it is to find the various layers and strata of the seabed, then use low frequency and wide beam. And if your purpose is to locate a cable and pipeline, then use high frequency and narrower beam. And if you want to achieve both, then choose something in between. Now if you want to study how big your beam width will be and how much footprint it will have on a seabed, you can use some formula and take a wise decision before you go for survey. Suppose the dia of a sub-bottom transducer is 120 mm and the operating frequency is 2 kHz. Suppose the general area depth is 50 meter and we take the sound velocity as 1500 meter. Then your beam width is going to be just under 60 degree and your footprint on the seabed will be 16.35 meter. Now if you change your frequency to 7 kHz, the beam width will be 13.6 degree and the footprint on the seabed will be 8.34 meters. You can use this formula to calculate your beam width and footprint. Beam width or theta is equal to C divided by F multiplied by D, where C is the average sound velocity in water column, F is the operating frequency and D is the diameter of the transducer. And the formula for footprint is equal to 2 multiplied by D multiplied by 10 under bracket beam width divided by 2 bracket closed multiplied by water depth, where D is the diameter of the transducer. Have you seen that sometimes you get a very narrow hyperbola reflection of the pipeline and sometimes we get a very wide reflection? So what's happening here? Let's first understand how you get this kind of a hyperbola graphics in your sub-bottom profile. We think that seismic energy propagates like this energy wave. Yes, it is, but to understand clearly, let's put a beam in there. So you see, outer or leading edge of the beam is touching the pipeline, but the position reference is the center of the beam, right? Say the vessel is moving to the right and here is our next beam. From the graphic, you can see that it has taken less time for the reflection to get back. And the green beam takes even less time than the previous beam. As the vessel moves ahead, one of the beam is reflected back quickest. And as the vessel moves away from the pipeline, the reflection takes more and more time to get back. Last reflection is from the trailing edge of the beam. Now let's draw a line through all the center beam positions. See, it creates a nice curve, which is bigger than the dia of the pipeline itself. The exact position of the pipeline will be the shortest beam that got reflected back quickest. And this is what is represented graphically on your chart. The size of the hyperbola does not represent the size of the pipeline. Now if you are going perpendicular to the pipeline, then you will get a nice crisp narrow hyperbola and it will be easy to pick the position of the top of the pipe. But if you are going at an angle to the pipeline, then you will get a fat, wide, big hyperbola and picking out positions will be very difficult. Now there are many variables that can affect the quality of our data. Location can be very noisy. Size of the pipe can be very small and may be buried with rock backfill. Irregular movement of the vessel and they can degrade our data quality and make it difficult to locate the pipeline. Understanding what happens during a survey operation, how an equipment operates best, what are the working principles and being prepared for every circumstances can make the quality of the survey much better. I hope we learned something new today. Did I miss something? Let me know in the comments. Always ask questions and try to learn at least one new thing every day. Ciao, I'll see you around.